Good morning, calculus people. This is the first video for section 3.3. There will be one additional video tomorrow. And this one, as you can see here, is we're talking about finding increasing and decreasing intervals and how we can use the derivative to do that. So it is not new for you all to talk about increasing and decreasing intervals. If you were given this function last year and you were told, find the intervals on which the function is increasing or decreasing, as long as we have the x values of the maximum minimum, which I gave you here, the 2 and the 5. So you could certainly say, based on this picture, this function is increasing on the interval from -infinity up to 2. And it's also increasing from 5 to infinity. Remember, we're talking about x values. So this function is increasing on that interval and increasing on that interval. And then this particular function is decreasing on the interval from 2 to 5, which would be this and this interval there. So you've talked about that before. Well, now we're just going to relate that to the derivative. So what do we know about the derivative while a function is either increasing or decreasing? So I've got the same picture here. So we let's see. Let's draw some. Let me draw some boundaries here and there. So let's talk about the two increasing intervals, which are the two extreme intervals here. If I draw a bunch of tangent lines, what do I know about all those tangent lines? All those tangent lines, and also over here, like I'm trying to draw tangent lines, on the intervals where the function is increasing, the slope of all these tangent lines is positive. The slope is positive, the function is increasing. And then similarly, if I draw these tangent lines here, what do I recognize? That interval, the function is decreasing. And what do I see about the slopes of the tangents in that interval? They are all negative, which means the derivative is negative. So the slopes here are negative, and back over here, the slopes are positive again. So that conclusion just says this. And this is an important conclusion. There'll be a lot of important conclusions. The goal of the task will be just keeping track of them all. This says if f prime of x is greater than 0, f of x is increasing. And if f prime of x is less than 0, f of x is decreasing. And the way that I have that in my brain, if the derivative is positive, the function is increasing. That's what that first sentence says. If the derivative is positive, the function is increasing. And then the second sentence says if the derivative is negative, the function is decreasing. So those two conclusions need to become pretty automatic in your brains. If the derivative is positive, the function is increasing, and if a derivative is negative, the function is decreasing. So now what we can do here, and what you'll be asked to do in this section is, given a function, it just asks you to find the intervals on which the function is increasing or decreasing. And by that, I do not mean with a calculator, graph it and find the maximum. We're doing this without a calculator, remembering that half of your AP test without a calculator. So here is the process for how to determine intervals on a function which is increasing and decreasing. So step one, locate the critical numbers. We did that earlier in this chapter. The critical numbers are any number where the derivative either equals 0 or is undefined. So we have to find those critical numbers. Step two says use those numbers to create intervals. What I mean by that is, like, if the critical numbers were 5 and 7, actually go back to my picture here. My critical numbers were 2 and 5. So we're going to take the entire number line from -infinity to infinity and break it into intervals using the critical numbers as boundaries. So if my critical numbers were 2 and 5, my intervals would be from -infinity to 2, and from 2 to 5, and from 5 to infinity. So we're going to create intervals based on these critical numbers. And then it says choose a test value in each interval. We're going to take each interval, and we're just going to pick any x value in the interval. Doesn't matter which one. What you'll see here is we want to pick one that's going to be easier to evaluate. But think about it. If for the entire interval, if I pick one number and I see whether the slope or the derivative is positive or negative, it's going to be true for the entire interval. So we're going to choose a test value. We're going to determine, step 4 says determine the sign of f prime of x for each test value. And then based on that sign, determine whether the interval is increasing or decreasing. So we're going to kind of make a little, like a sign chart kind of, and we'll be doing this a bunch in this chapter. So this is your first exposure to this, and but it'll happen a bunch. So all I have left here, I have two examples where the task is, here's a function, figure out the intervals on which the function is increasing and on which the function is decreasing. All right, here we go. First one is this. Determine the increasing and decreasing intervals for the function f of x equals x cubed minus 3 halves x squared. Well, step one says find the critical numbers, which is where the derivative either equals 0 or is undefined. So let's find the derivative. The derivative of this function is 3x squared, and then 2 times 3 halves is 6 halves, which is 3, so minus 3x. There's the derivative. The critical numbers are where that derivative either equals 0 or is undefined. Well, that derivative, 3x squared minus 3x, is never undefined, so I need to know where it equals 0. So I'm going to set it equal to 0 and solve it for x, and I see a GCF of 3x, which leaves me with x minus 1 equals 0. Now, let me point out that the derivative, that this is absolutely the derivative of this function, but really so is this. And I point that out now because in a minute we're going to want to go back to the derivative, and I'm going to convince you that it might be easier to look at the second one. But those are really both derivatives. Now let's keep solving for this. So this, of course, leads to the critical number x is 0. This leads to the critical number x equals 1. So I have two critical numbers, 0 and 1. Help me. There we go. So we are going to now create what I'm calling this a sign chart when we need intervals. So those are my two critical numbers. So now my table looks like this. First, I have my intervals. The first one in this case goes from negative infinity to 0. The second one goes from 0 to 1. And the third one goes from 1 to infinity. I am using my critical numbers to create intervals with my critical numbers being the boundaries. And I'm going to pick a test value. Like, let's pick a number inside each interval. And again, in a minute, we're going to try and evaluate the derivative at this number. So we want to pick as easy a number as possible. So when we can't pick the critical numbers, it has to be in the interval. So between negative infinity and 0, sorry, my lights went off again. Between negative infinity and 0, I might pick the test value negative 1. And between 0 and 1, I guess I'll have to go with a half. And between 1 and infinity, maybe I'll pick 2. I am just picking a value in each interval. Okay. Now it says determine the sign of the derivative for each test value. So I want to figure out the sign of f prime. I want to plug in each number into the derivative. Now, here's where I said, so like for instance, the first is negative 1. I'm trying to find f prime of negative 1. And maybe you can do this in your head. Maybe you have to write it out. Either way is fine. Let me go back up here to my derivative. To find f prime of negative 1, I could either plug it into that version of the derivative or that version of the derivative. Remember, I don't really care what the value is. I just care whether it's positive or negative. All I care is about the sign of the derivative. So it turns out that if I use the factored form, if I plug in negative 1, let's just figure out for each factor whether it's positive or negative. I'm plugging in negative 1. 3 times negative 1 is negative something. Negative 1 minus 1, in terms of negative 2, is also negative something. I've got a negative times a negative, which means my answer is going to be positive. Do I know exactly what positive number? No, and it doesn't even matter. So it's tempting here to do too much work. If you were to go into the original derivative, which is this up here in yellow, and plug in negative 1, you get the answer is, I think it might be 6, but it's positive something. But the factored form is going to be easier. I'm plugging in negative 1. I have those two red circles there. 3 times negative 1 is a negative. Negative 1 minus 1 is another negative. A negative times a negative is in fact a positive. As we go down here, I'm going to just put a plus sign there. That means the sign of the derivative of negative 1 is positive. What about 1/2? I'm going back up here. Now I'm plugging 1/2 into these two circles again. 3 times a half is positive. I've got a positive there. And 1/2 minus negative 1 is negative. I've got a positive times a negative. And a positive times a negative is negative. That's all I care about is that it's negative. Do I care exactly what negative? I don't. So it turns out to be whatever, 3/2 times negative half, negative 3/4, whatever it is, doesn't matter what it is. We need the sign of it. It turned out to be negative. And then lastly, let's take the number 2, which is in my last interval, and plug it into the derivative, going back to the factored form, which is these 2 red circles. And if I plug in the number 2, 3 times 2 is positive. 2 minus 1 is positive. I have a positive times a positive, which in fact is positive. Which leads me back to here. Now, warning, oftentimes they do alternate from positive to negative, but absolutely not guaranteed to do that, so don't jump to any conclusions. So, give me one more line on my table here. Now it says, based on the conclusions, now figure out the interval. So let's talk about each of these intervals. The first interval is from negative infinity to 0. Since the derivative is positive in that interval, again, we go back to the conclusions from the beginning. If the derivative is positive, the function is increasing. From 0 to 1, this middle interval, since the derivative was negative, the function is decreasing. And the third interval, since the derivative was positive, the function is increasing. Now, the AP test is going to be picky. Putting a sign chart on the AP test is a great idea. Make sure you then answer the question. So the question says, where is this function increasing? It is increasing on the intervals from negative infinity to 0 and from 1 to infinity. And where is this function decreasing? It's decreasing on the interval from 0 to 1. And if you had to justify that, you'd say the function is increasing because the derivative is positive on those intervals, and the function is decreasing because the derivative is negative on those intervals. And of course, that graph does look like it's just it's a cube like this and this and this. So that x value must be 0 comma something, and that x value must be 1 comma something. So it's increasing to 0, then decreasing to 1, and then increasing to infinity. So that does match with what we just did here. Sometimes you'll know what the function looks like. That might help the cause. Sometimes you don't. All right, one more example. Same instructions. Determine the increasing and decreasing intervals for that function. Now, do we know what that looks like? Maybe we do, maybe we don't. All right, so process is the same here. We are going to find the derivative. Looks like I have to use the quotient rule. So the derivative of that function is the bottom, which is x plus 1, the quantity squared, times the derivative of the top, which is 0, minus the top, which is 1, times the derivative of the bottom, which is 2, little chain rule, times x plus 1 to the first, times 1 officially, the derivative of that, all over the bottom squared, which is x plus 1 squared squared. Now I can clean that up a little bit. That becomes 0. Let's see here. Looks like I have negative 2 times x plus 1 on top over x plus 1. What's that, to the fourth in the bottom? Ooh, I can cancel one factor of x plus 1. I end up with negative 2 over x plus 1 cubed. That is the derivative of that function. Well, I need critical numbers. I need to know where that derivative either equals 0 or where it is undefined. For a fraction to equal 0, the top would have to equal 0. Well, the top of this fraction is negative 2, and negative 2 never equals 0. So this derivative never equals 0. But where is it undefined? Well, I think we can clearly see that if x were negative 1, the bottom would be 0, which is a problem. So my critical numbers is that x equals negative 1. Turns out, I think there's an asymptote at that. I'm looking at the graph, but surely the derivative is not defined there. So I only have one critical number, which means I have, again, the process says take the critical number and create intervals. Well, here's my interval. I only have one critical number. It was negative 1, negative infinity, negative 1. And then the other interval is negative 1 to infinity. There are my two intervals. I now need to pick a test value. Like, let's pick a number in each interval. Well, from negative infinity to negative 1, I would argue negative 2 might probably be the easiest. From negative 1 to infinity, since 0 isn't a boundary, I think 0 is, I think for sure, going to be an easy number to evaluate. So I picked a value in each interval. Now I want to figure out the sign of the derivative. And I'm taking those two values, negative 2. Well, let me go back to my derivative, which was here. Let's see, my derivative is here. And I'm evaluating that at, what was it, negative 2 and at 0. Well, I'm trying to find, again, you might do this in your head, but I'm trying to find f prime of negative 2. That would equal negative 2 over negative 2 plus 1. That's a negative sign cubed. In particular, that's a negative on top, and negative 2 plus 1 is a negative, cubed is a negative. I have a negative divided by a negative, which turned out to be positive. So I go back here, and I figured out that the sign of f prime was positive there. I don't know, did that draw underneath my picture? Oh, it did. That's pretty cool. Okay. And then what about plugging in 0? Let me go back here and back here. If I plug in 0, I get negative 2 over 1 cubed, which is a negative over a positive, which is a negative. So since the derivative is positive in this interval, the function is increasing on this interval, and it's decreasing on this interval. So where is this function increasing? On the interval from negative infinity to, not to 0, to, was it to negative 1, I guess it was? To negative 1. And this function is decreasing on the interval from negative 1 to infinity. And if you wanted to check your work, this one does, in fact, have an asymptote at negative 1. And it looks like this and then this. So sure enough, it's increasing until negative 1, decreasing from negative 1 to infinity. So again, at the moment, we are using the derivative and this sign chart thing to determine intervals on which a function is increasing and decreasing. The only thing we're going to add to that in the second video is how to take this one step further, and then from everything we've just done, determine where there might be maxes or mins of the function. But that's for tomorrow. So your homework, the instructions are just what it says. It says, I'm reading right out of the book. It says, in exercises 9 through 20, identify the open intervals on which the function is increasing or decreasing, which is exactly what I just did to those two examples. So that's all I've got. Have a great Monday.